Hello everyone and welcome to the 58th lecture of the course Advanced Structural Analysis. This is the last week of the course and we are discussing the problems related to the material nonlinearity in the given system. While having the previous discussion, we have understood that the approach of having the problem and solving the problems based upon the material nonlinearity is very much similar to what we have done for the geometrical nonlinearity in the given system. Only the user need to identify very efficiently and carefully the basic material rule, that how the material nonlinearity in terms of the general stress strain relationship occurs in the given problem. And once that basic idea of the material relationship is known, the remaining part of the procedure is more or less similar to the general iterative and the incremental analysis approach which we did in the geometrical nonlinearity. So, we will try to continue with the discussion on the evaluation of the residue for the iterative solution schemes. We have briefly seen some of the content related to the general stress strain behavior. What we have also understood in the given system, that as we look at the given problem, the nonlinearity is introduced from the stress strain relationship of the material response, which is given in terms of the general internal variables of the system, which are the stresses and the strains of the parameter. Whereas the general introduction of the matrix approach or the general analysis of the system is done on the overall variables of the system which are available at the respective nodes of the given problem, and those variables primarily happen to be the displacements or the forces of the given system. So, the effective parameters on which we try to make the increments or the changes, those appear on the external system as the loads, whereas the philosophy of the nonlinearity is introduced in the problem through the way of increments in the stresses and the strain parameters of the given system. So, there has to be a good connection between the external system, which is the load and the displacement system, and the internal resistance system, which is the stress and strain parameters of the given system. So, looking at that philosophy, we came up with the general behavior where the identification of the stress and strain relationship was identified, and then we also looked at the formulation of identifying the general stiffness of the system, which can be identified in terms of the displacement parameters of the given system, and based upon that we can also identify the respective nodal load vectors, which happen to be the qualifying criteria to check the suitability of the given system for any kind of corrections required in the overall approach. So, we will try to see it now with the stress increment first, which we have briefly discussed in the last session. So, as we say that when the given system is subjected to a kind of a nonlinear strain hardening, where if I say that the original system is undergoing some deformation, the stress strain relationship, and that follows the path which is O to A, and then at the point of A we draw a tangent on the system. So, one thing we must understand, that point A is well above the initial yield of the given system. So, it is always it is already in the nonlinearity of the given system, and somewhere on this point A we are trying to calculate now the tangent of the given system, and that is somewhere drawn as a tangent having the slope equal to E t in the given system. Now, with respect to this given tangent, the overall increment in the stress appears to be sigma n plus 1 prime, which is with the increment value of d sigma n dash in the given system. Now, corresponding to that, the user can also identify that what is the value of the strain parameter in the given system, and now we realize that the given strain parameter, which will be identified corresponding to the defined increment value on the system, when we correlate it with respect to the general relationship of force, the general relationship of the stress in terms of the strain parameter of the given system, the user will realize that corresponding to this parameter of the strain, the respective amount of the stress is sigma of n plus 1, and that is relatively lesser than the original value which is initially identified by constant slope on the given system. So, now we need to make a correction of this much amount, so that the effective value which is being predicted by this increment on the system by sigma n plus 1 prime can be come down to the actual value of the stress which is available as sigma of n plus 1. Now, to account for that, we also evaluate based upon it the plastic strain parameters. So, the overall system at this point where the sigma n plus 1 lies, from there we try to draw the reversal load unloading path on this system, and this unloading path at the level of say the initial position of the given system at which we have initiated the deformations, or at which we have drawn the tangent matrix of the given system, we identify the component related to the elastic component of the strain and the plastic component of the strain in the given system. So, based upon this idea, we are able to identify the plastic strain parameter on the given system, and that is typically described with respect to the original elastic strain in the original strain in the given system, the overall strain which is adopted based upon the stress increment on the system, minus the corresponding value which is sigma of n plus 1, which is the value at this level, minus sigma n, this corresponding difference in the given system, divided by E. So, the effective initial elastic modulus of the system which was defined for the given problem, based upon that we evaluate the effective elastic strain on the given problem, and that typically we remove from the overall strain value to calculate the plastic strain parameter of the given system. Now, once the user is able to do it, we have also tried to see, we have also seen that in case of the constant value of the ET, where the system follows, even the original curve does not follow the relationship with the non-linearly varying strain hardening, but whereas it is a constant strain hardening part. In that situation, the point C will actually coincide with the actual point, which is somewhere over here. So, if I define this point as a D point in the given system. So, if the point C and D coincide with each other, we realize that the corresponding relationship which is being written over here can finally reduce to the expression like this, where sigma of the strain increment in the system corresponding to the plastic parameter is now equal to C times the overall strain in the given strain increment in the given system, and this parameter of the C is defined as 1 minus Et upon E in the given problem. So, using this idea, the user can now identify that corresponding to a system in which the plastic strains are introduced, and also the system in which the elastic modulus changes regularly and continuously throughout the nonlinear range on the system, the effective value of the plastic strain can be defined by either this relationship, or in case where the elastic modulus in the nonlinear or the plastic range becomes a constant value, which means it follows a more or less a bilinear kind of a profile, we come up with the simplified form of the expression to give the plastic strain parameter of the given system. Now, this given parameter which we have just described becomes little different when there is a situation where the system is initially loaded from a point which is below the initial yield point of the given system, because this part of the system will elastically deform. So, it will not generate any amount of the plastic strain in the given system, whereas the system which will deform beyond this point, beyond the point F on the given system, will deform plastically. So, what this actually means that if the user is initially trying to draw the tangent at the given point A, the tangent will be drawn with respect to the initial slope of the system, which is the linear elastic property of the material, and based upon that the user will make the initial point somewhere over here. So, we can call that this is the point D of the given system. So, based upon this given point D which is located, the initially predicted value of the stress increment or the stress value will be sigma n plus 1 prime, and this is the amount of the stress increment which has been provided to the given system. But now, when we calculate that corresponding to any of the point where the yield has taken place on the system, the tangent stiffness on the system will reduce from the initial value of E, and now it will become the updated tangent modulus. Say if I come up with the constant value E of t in the given system. So, corresponding to this new tangent line, the stress parameter will be somewhere predicted lesser than the original value which has been predicted by the first parameter of the given system. So, now the original curve of the given system with respect to the same strain parameter, the strain parameter which is obtained with respect to the sigma n plus 1 prime on the original first increment of the stress system, we realize that the original stress value in the given system somewhere lies with the value sigma of n plus 1. So, there is a requirement that when we are trying to evaluate the plastic strain parameter for this problem, we should take care of the possibility that the range which is between the sigma of n, the initial point where the initial tangent was drawn to the initial yield point of the system. Between this, the inclusion of the plastic strain parameter which has been adopted in the problem need to be removed, and that particular part is typically done by considering that the actual plastic strain parameter of this given problem will be corresponding to the given point which is located over here. So, if we define that this point somewhere over here is a point E in the given system. So, I draw a line which is with the initial slope of the system which is E, and that comes back to the system at this level where the yield in the system initially starts. So, we define that this initial distance which is f k is the effective plastic strain parameter in the given system. And now, in order to define it, we have to calculate the value of f of g in the given system minus g of k in the given system. So, evaluating these parameters will give us the actual plastic strain parameter of the given system. So, through a simple modification we can evaluate the value of f of g. So, f g can be either calculated by this expression the way it is written a b minus b h, or f g can also be calculated by considering that this overall dimension or this overall length of the strain parameter dimension can be equal to corresponding to the increment in the stress, which is, so if we define this value, this can be written as sigma of n plus 1 prime minus the stress level over here which is sigma y naught in the given system, and divided by this portion is having a constant slope or the initial slope of the given system which is E for the given problem. So, the user can simply define that this value will be equal to f g in the given system. So, the initial f g value corresponding to the total length from here to here can be evaluated as the difference between the sigma of n plus 1 prime minus sigma y naught divided by the elastic modulus corresponding to this profile or this linear profile of the given system, which is initial modulus of the system E in the given problem. Now, through a simple modification one can identify that sigma of n plus 1 prime which is located with respect to this point can also be defined in terms of the parameter of the overall strain parameter of the system. So, d of epsilon n. So, in order to get that parameter, what we can write here is that sigma of n plus 1 prime minus sigma of n, which is the initial point over here, and corresponding to that we get the expression that this is equal to E times epsilon or the change in the system d of epsilon n in the given problem. So, using this expression, now the user can easily convert the value of sigma of n plus 1 prime in the given system, which comes out as sigma n plus E times d of epsilon n in the given problem, and by substituting this expression in this value we get a very simplified form of the expression which appears like this, and it can be considered that this expression of f g can be further written as d of epsilon n minus, or d of epsilon n if we take constant it comes out as 1 minus sigma of y naught minus sigma n upon E, and at the same time d epsilon n is not available over here. So, we also divide it by d epsilon n, and this becomes the expression which we can simplify and write as d epsilon n 1 minus m in the given system. So, this representation comes out with the value of m in the given problem. Now, we can further consider that the expression of the expression of g k in the given system, and once we evaluate that part of the expression also in the given system, we finally see that the overall f g expression or the epsilon p expression of the system can be written as c times 1 minus m into d epsilon n in the given system, which means that in the case when the system has a linear stiffness part which is defined by this particular value beyond the initial yield, the condition of the system. So, we are now identifying, of course, this particular relationship is defined in a situation where the elastic modulus beyond the yield is considered to be a constant value, and that is defined by the E t parameter in the given system. So, we realize now that the plastic strain parameter at a point, if it is below the initial yield point of the given system, so that need to be evaluated correctly with respect to a expression which is defined over here, and this is a bit different than the actual expression which we calculated previously. So, if you start with the point which is above the initial yield point, say the yield point is over here and we start with the tangent at this position, even with the constant value of Et, we end up with the plastic strain which is C times d of epsilon n. But the moment we start with the tangent which is below the given yield point of the system, so we must take the correction for the initial linear profile of the system which will not contribute to any plastic strain, and that is where the expression comes out as C into 1 minus m times d of epsilon n. So, we will be trying to use these expressions in the later part as we proceed with the numerical problems on the given system. Finally, there is the third case in which also we need to make the consideration for the corrections, and that is the case when the unloading occurs in the given problem. So, as a simplistic case, we start with the given profile of the loading, we go up to certain point, say the point A over here, and at this point the initial say stress level is defined as sigma n, corresponding to which the strain is also identified as epsilon n. Now, at this point the user want to make a small change in the strain parameter. So, let us as we are doing it with the unloading parameter. So, rather than increasing or rather than going with the stress increment in the given problem, we can come up with the change in the strain parameter of the given system. So, at this point the user tries to make a change in the strain parameter, say a value of d epsilon n in the given system, and now with respect to this change, if I draw the tangent modulus at this point, it will follow the curve like this, and it will show me the value corresponding to this new updated strain increment will be equal to somewhere over here, which is sigma of n plus 1 prime. But as I realize that the path which I have followed is corresponding to the loading path itself, whereas the position of the system or the consideration of the system is corresponding to the unloading path. So, the correction will be required in which the original system will be drawn with respect to the elastic modulus E, which is the initial modulus of the given system, and corresponding to that we have to figure out that wherever this system intersect, that will be the respective value of the actual stress parameter in the given system. And we can now identify this value of sigma n plus 1 directly, because we realize that this modulus is a constant value in the given system, it is not changing in the given profile, and as it goes through this unloading profile, we can evaluate this drop in the given system from the original value of sigma n as sigma of n minus sigma n plus 1 is equal to the respective value of the strain parameter. So, that typically will come out as minus of E times d epsilon n. Why we have written d epsilon n with the negative? Because we are taking it with the opposite direction in the given system. So, if you just take now the geometrical consideration in the system, it can be written as sigma of n plus 1 is equal to sigma n plus E times d epsilon n in the given system. So, using this idea, the user can evaluate the standard value associated with the new stress increment in the given system, and that gives us the effective value corresponding to the stress level on the unloading profile of the given system. But we also realize that the decrease in the stress level with the unloading profile will not result into any kind of change in the plastic strain parameter or any contribution to the plastic strain parameter of the given system, which means that the total contribution of d of epsilon n which has been obtained in the system is the total corresponding to the elastic parameter of the system, whereas the plastic parameter in the given system is completely 0 in this case, as the recovery of the unloading profile will result into a complete elastic recovery in the given system. Now, knowing these profiles, we now move to see that how the iterative schemes utilize these criteria in the given analysis. So, as a first scale test, we must know that what is the way to identify the difference or the error in the given system. Now, why it becomes important? Because if you see all these differences which we have just discussed, we are defining everywhere the error with respect to the differences in the stress level. So, if I just want to go with this expression, I say that the initial tangent has been drawn with respect to this value which crosses at the D, whereas the actual curve somewhere passes through the updated tangent at each and every point and somewhere crosses at C. So, this is the difference in the stress level which we will get corresponding to the predicted value of the strain. But now, to be very careful about the overall analysis of the system, we are not doing the analysis based upon the increment in the stress values in the original system, whereas we are applying the load in the given system with respect to which the respective increments are being applied. So, what user need to also identify that corresponding to the value of the strain which has been obtained, say the epsilon n plus 1 at any particular instance of the given system, I can obtain the value of sigma of n plus 1 based upon the given stress strain relationship, and that is how the general expression will be utilized. Once I know the value of the stress parameter in the given system, what user should also be doing, corresponding to this stress profile, the user should calculate now the total nodal load vectors of the given system. So, once I know the nodal load vectors in the given problem, then I can correlate them with respect to the actual applied load in the given problem. So, the understanding is that we applied certain load, say F1 and F2 in the given system, or I would rather say not to confuse it with the representation which we have given later on. Say I apply the load as P1 and P2 in the given system. As I apply the initial load with after the increment as P1 and P2, after doing the nonlinear analysis, I calculated that the internal stresses in the member happens to be sigma n plus 1, corresponding to which, after doing the calculation as we do for the force evaluation, we calculate that in any given member the amount of the force is A of m sigma n plus 1 into volume integral of the given system. Now, this value of the stress is the actual stress inside the given member. So, in each of the member we have evaluated that what is the amount of the stress in the given system, and corresponding to that stress the user is able to calculate what are the nodal forces in the given system. So, these nodal forces corresponding to the given member 1 will be identified. Similarly, the nodal forces corresponding to the member 2 will also be identified, and similarly the nodal forces corresponding to the member 3 will also be identified. Now, I can take the sum of all those forces and calculate the net nodal force corresponding to the step n plus 1 in the given system. So, by taking the sum of all the forces at this particular joint, I can just write the summation of the net actual load which is actually identified at this particular point in the given system. What we will realize that the value of F1, so I am just now writing the values corresponding to the direction of P1 and P2, and those values as per the actual will come out as F1 and F2 in the given system. And what we will realize that P1 minus F1 is having certain difference, and that is our residue 1. P2 minus F2 is also having some residue, and that is our residue 2 in the given system. So, what we are effectively looking as a residue in the given system is described with respect to the external system, and to evaluate that we have to identify the internal strains in each of the members. Corresponding to that, I have to convert these stresses, and once I know these stresses in the members, I have to convert them into the equivalent nodal loads of the given system, and by taking the sum of all those loads, I have to take the residue of the given problem, which will tell us that whether the correction is required in the given system, or whether the system is well within the required limit of the tolerance. So, this is the primary way in which we define the residue in the given problem. Now, as far as the use in the iteration is concerned, we typically consider that for any of the n plus 1th node. So, at the same position as we are defining P of 1 or P of 2 in the system, of course, these are the values which are applied from the external part, but what one can also do, one can also consider that these submissions are nothing but these are the summation of A transpose sigma of n plus 1 prime into dV, which means that if you just follow the simple line based upon your tangent modulus on the system, wherever it goes and strikes to the given stress diagram, and I take that value of the system without any correction, corresponding to that the value of the load on the given system is identified as P of n plus 1. Of course, this is not required to be calculated because this value will be known to the user. We have provided this as external load, but once we have calculated the value of n plus 1 for the force parameter at the nodal load positions, we will calculate this value, which is the correction required in the given problem. Now, we start with say the first iteration step in the similar manner. As a first iteration Kt n plus 1, which is the now the stiffness, the overall tangent modulus identified at the n plus 1th step of the given system, and then we provide this value of the residue in the system to calculate the increase in the nodal displacements of the given system. So, this is of course, this iteration we are calling is the first iteration or the part of the iteration, but this is taking place at a position where already say we have obtained that this is sigma of n epsilon n, this is sigma n in the given system, and corresponding to that we were able to obtain that at n plus 1th position somewhere over here the system is able to predict the value which is the higher value of the system, whereas the actual value is sigma of n plus 1 in the given system. And corresponding to this sigma of n plus 1, we have obtained now the member forces, the nodal load forces of the system, subtracted them with the actual load which is applied on the system to get the residue value on the given problem. And now with this expression, I will be able to calculate that what is the required amount of displacement change which is needed to be provided to the system to correct this error in the given problem. The moment I get this difference corrected, say the user evaluates the dun star value in the given system, we provide this dun star value to evaluate u of n plus 1, and that can be simply done as u of n plus 1 equal to u of n plus du of n star in the given system. And this value of the u of n plus 1 which has been obtained in the given system will now be utilized as the value corresponding to the updated displacement of the given system. Of course, now we will try to briefly see this part of the procedure in a simplistic algorithm so that we can understand this. So, to start with the given system, we can have initially initial point. So, this is the original profile of the system. Say we are starting with this position in the given system. So, somewhere at this position we calculate that epsilon n and the sigma n values, these are known to the user, and corresponding to these values the user has drawn a simple tangent on the system with respect to the tangent modulus E t, which is the tangent modulus evaluated at this particular point of the given stress strain curve. Now, as we have obtained this value corresponding to this given system, we provide a stress increment in the given system, and with respect to that stress increment the value, say somehow comes out as the value over here. So, this is the value which is predicted as sigma of n plus 1 prime in the given problem. Now, with respect to this value, the actual strain in the given problem, if we evaluate, is epsilon n plus 1, whereas the given value is not on the actual curve on the system will be predicting a different value of the stress parameter, and we call it as sigma of n plus 1. So, as a part of the procedure, what the user will do, we evaluate first the change in the strain parameter as a first part of the iteration, as we are trying to correct the system. So, rather than calling it sigma of epsilon of n plus 1 directly, I will call it epsilon of n plus 1 of 1, which means it is the first iteration in the given system, and I will provide here d of epsilon n 0, which is the first or the 0th iteration on the given problem which has been done. So, the value of d epsilon naught, the moment it has been obtained corresponding to the given system, can be provided to evaluate the value of n plus 1 at the position 1. So, we write it as this is equal to epsilon n into d of epsilon n naught in the given problem. Now, with respect to this given value which is obtained in the given system, the user will be able to calculate sigma of n plus 1 in the given system. Now, once the sigma of n plus 1 is obtained based upon the general relationship in terms of epsilon, we evaluate this value to calculate the effective member forces in the given system. So, we call it as that f of n plus 1 with the first iteration in the given system will be evaluated, and that value will come out as A transpose sigma n plus 1 into d of v, the volume integral of the given system. So, this will be evaluated as the nodal load vectors for each of the member, and as we are doing for each of the member by taking the submission for all. So, we will also write over here that this is the net submission for all the members with respect to the individual nodes, and that value is identified as the f of n plus 1, the n plus 1th node of the given system at which the value is obtained, and this is the first iteration in the given system. The moment we get this value, we will try to take the difference of this value with respect to p of 1, which is the corresponding increase in the or corresponding value of the load which has been provided, and take the difference of this with this given value in the system. Of course, this initial value of the system will also be, as we are now already including the load increment in the system with respect to the initial point n. So, the load increment with the new position will be n plus 1 in the given system. So, the difference is p of n plus 1 minus f of n plus 1 with the first iteration in the given system. And now, this value should be equated with the kT, which is the tangent stiffness of the given system, which has been or which need to be evaluated with respect to epsilon of n plus 1 and this is also with respect to the first iteration in the given system. So, we got the first iteration value corresponding to which we evaluated the kT value in the given system, and once this value has been obtained, we just consider the d of u n 1 in the given system. So, initial value which we have defined in the system, that was say corresponding to the d of the 0th iteration. So, now the value is identified with the first iteration in the given system. The moment we provide this value, we will be of course, this value will be now known to the user, this value is also known to the user. So, the value of the change in the displacement, nodal displacements can be obtained. So, if we define the d of u n 1 in the given system, we can identify that. So, once we obtain this value, we can calculate u of n plus 1, the updated value of the displacement at the nth node in the given system, and that will be defined as u of n, which is corresponding to the previous node in the system. So, this was earlier with the 0th iteration, and now we have added the first iteration value in the given system. So, this is the first iteration value which is corresponding to the u of n plus 1th node in the given problem. Now, the moment we have obtained this value in the system, we go back again to calculate the respective strain parameters in the given system. So, we again calculate the epsilon n plus 1 in the given system. Corresponding to these values, we also calculate the d of epsilon n in the given system, or we better call it as d of epsilon n 1 in the given system. So, the first increment which was provided was d of epsilon n naught 0, and now we will identify the next increment in the system, which is d of epsilon n 1 in the given problem, and corresponding to this increment, the value will be identified. Of course, we have already calculated this value as a second slope over here when we are calculating this expression, and with respect to that, now the second iteration or the second increment in the strain parameter, once I define in the given system, the user will be able to predict the new parameter or the new value in the given system, and that can be reflected by the point somewhere over here. So, based upon this parameter, the user has now calculated the value which is corresponding to, of course, the same point, which is sigma of n plus 1 prime, but with respect to the original curve, the value over here has now modified, and that value can be now called as sigma of n plus 1 of 1 in the given system. So, after the first iteration, we have got the new value in the given system. So, I can call the original value or the previous value as sigma of n plus 1 0 in the given system. So, once we have obtained this value, we can again now calculate corresponding to this value the new correction in the system. So, we evaluate that corresponding to f of, so based upon that we evaluate now first the epsilon of n plus 1 with the second iteration, and with respect to this value we obtain the corresponding value of the stress, which is also n plus 1, and we better call it also as a 2, because let me say that this is the value of the second iteration, this is the first iteration, and once this value is obtained in the given system, we can identify the corresponding value of the force again with the second iteration in the given system by taking the summation of the A transpose sigma of n plus 1 with the second increment and the volume integral. So, this way we are now able to identify again the value with respect to the next force increment in the given system. To define the residue, again we will come up with P of n plus 1 minus f of n plus 1 with the second iteration in the system. We will again see whether this value is less than the tolerance. If it is still not lesser than the tolerance value, we will again go with one more level of increment in the given system. So, this is the brief procedure which we typically identify, as we have just defined here, that we define the initial solution. Based upon the initial solution of the given system, we come up with the evaluation of the strain increment in the given system, which are defined in terms of the displacement, nodal displacement increments of the given nodes, and based upon that we obtain the first change or the first increment value in the given system. Once we identify these values, we calculate the respective value of the stresses in the given system, with respect to which we identify the respective forces, and once we define the respective iteration in the system, we go with the successive iterations to check whether the next set of iteration is required, or we can stop at this particular iteration to give the solution of the given problem. So, with this we stop over here. We will start with one example case in which we will try to define a simple problem of a bar first, in which the axial load can be applied say with some value of f, and as we know that if the cross section area of the system is given, the force or the stress can be defined as sigma equal to f upon a in the given problem. At the same time, the user can also define the strain in the given system, which is identified as the change in length upon L of the given system. If I define the original length of the system is L, and this value of delta can be written in terms of the simple relationship of the elastic modulus of the given system, and we know that the stress value can be defined as so we can write from here that AE upon L, which is sigma upon A, which is the f upon A, which is the amount of the stress in the given system, is equal to E into delta upon L in the given system. So, from here the user can identify that the delta value can be identified as the FL upon AE in the given system. So, this will give us a proper measure of the strain parameter on the given system as f upon AE in the given problem. And once we have this measure in the given system, now we can identify that what kind of material rule we are using. So, as a simplistic procedure, one can go with a bilinear form of the expression, and we can have say initial yield value say sigma naught defined for us, corresponding to which the strain parameter also is known to us, say epsilon y. We can have the initial slope of the given system known to us, say the E value, and the second slope can be defined say E of t, which can be defined as a simplistic part as E by 2 or E by 3, which is say a fraction of the initial slope of the given system. And now user can start with some small increments in the given system, say the increment on the original stress of the given system, which are reflected in terms of the changes in the strain of the given system. But in the original system, the user will not be applying the stress increment directly, whereas the user will be applying the increment in the loads of the given system. So, what we do in the original system, we bring the idea of say the d of f, which is the change in the force in the system, a small increment in the force. As a starting point, we can say that the initial value of the so we draw it as f and delta relationship. We call that initially the delta value is also 0 and the force value is also 0 in the given system, and we apply the d of f, which is equal to say initial value of f1 in the given system. So, corresponding to this given value of f1, which is calculated as the first force increment in the given system, we evaluate that with respect to the value of f1, what will be the stress in the given system, and that value of the stress with force value of f1 will be equal to f1 upon A in the given system. At the same time, we also evaluate what will be the strain value at this point, and that value can also be evaluated as the strain will be equal to f upon AE in the given system. Now, based upon first the initial modulus, we will just try to calculate these two values of the given system, which means that we will evaluate the value of elastic modulus as the initial elastic modulus of the given system, and corresponding to that we can draw the simple profile. We can keep on drawing this profile till the point the system reaches to the yield value of the given system, and as the system reaches to the initial yield, we will modify the elastic modulus by the value of the ET in the given system, and this way we can update the respective set of displacements which are obtained in the given problem. So, to obtain the displacement, we can simply use the value FL upon AE, but we must realize that the value of E has to be updated the moment the value of the stress in the system will reach to the value which is greater than the yield value of the given system. So, till the point the sigma value is less than sigma naught, we will be okay to use the value of elastic modulus. The moment sigma becomes greater than sigma naught, we have to modify the value and we have to use it as ET in the given system. So, with this we stop over here. We will briefly see a larger scale of problem in the next session, so that we can discuss the implementation of the nonlinear material properties in the given system. Thank you everyone.